Hello, students with an infinite possibility. We are going to study the end behavior of graphs today, which means we will take the limit as x goes to positive or negative infinity for our functions. Now, fun things happen with some of our functions that are rational, and we might get some horizontal or oblique asymptotes as we examine the end behavior. So your lesson preview provided you with lots of opportunity to really explore what's happening with exponential functions. It's been a while since you played with those. That's why we had this preview. Hopefully you took e to the x minus 1 and set it equal to 0. Then you solved for x. And when you solve for x, you should remember that when you have e to the x equals 1, the inverse of your exponential function is your natural log. So the log and e cancel out. X equals the natural log of 1. Hold on, but the natural log of 1 is just 0. So the vertical asymptote occurs where x is equal to 0. Now for question B, as you are approaching infinity, that is just a sneaky way to build in the right tail end behavior. And hopefully you've filled in your table of values and figured out what the right-hand tail is doing. Now for question C, you were told to determine the vertical asymptotes. If you wrote the answer is 1, then of course you are incorrect. I was tricking you. All right, so to find your vertical asymptote, you want to take your denominator and set it equal to 0. So that your denominator equals 0 when x equals 0 plus or minus pi plus or minus 2 pi, and it goes on and on and on. Now, if you said the vertical asymptotes are 0 plus and minus pi, you were also not correct. So this is a sneaky little problem. Remember, you have a removable discontinuity at x equals 0. So that can't be a vertical asymptote. So your removable discontinuities at x equals 0, your vertical asymptotes will occur when x equals all values of pi k, where k is equal to plus or minus 1, plus or minus 2, and etc. Now, as you were filling in your table of values, when you write x is going to negative infinity, that is talking about the left tail end behavior of your graph. And hopefully you had no trouble using your calculator. Okay, so as we begin looking at the end behavior of graphs, that means we will be examining what happens as we go towards positive and negative infinity. The thing we must know in order for today's lesson to work is that the limit as x goes to positive infinity of 1 over x is equal to 0. Now, let's look at your data table. As you divide by larger and larger values of x, your answers are tending towards 0. You have a horizontal asymptote as you tend towards 0 on your graph. But more importantly, if you have one donut and 10,000 people, and you're all sharing the same donut, how much donut are you going to get? Very little donut. So if you take 1 and divide it by a big number, your answer is 0. All right, with that, let's talk about tail end behavior. Your right tail, if you take the limit as x goes to positive infinity for your function, that means you're looking at the right tail. If you take the limit as x goes to negative infinity for your function, that means that you're looking at the left tail. Now, two things can happen. You can find a horizontal asymptote for many functions, or your answer is going to go to infinity. Now, if they go to infinity, that means you probably have some sort of, you could have an oblique asymptote. All right. For the three functions I have here, we are going to explore what happens at both the right and left tails. So looking at f of x. Now, the thing I want you to notice is that the largest exponent in the numerator is x squared. And the largest term with the exponent is also x squared in your denominator. So if we multiplied by 1 over x squared divided by 1 over x squared, that's going to make this function a little bit easier to think about with our tail end behavior. So the limit as x goes to positive infinity, multiply through, we get 7 plus 4 over x plus 2 over x squared, all divided by 2 over x squared minus 3 plus 4 over x. Now remember what we just talked about a few minutes ago. As we go to positive infinity, 4 divided by infinity goes to 0. 2 divided by infinity squared, that goes to 0 as well. Oh, here's another one and another one. So what we can do is rewrite the problem. It's the limit as x goes to positive infinity, 7 over negative 3. And you know the limit of a constant is equal to the constant. All right. Now, this multiplication works every time to simplify these rational expressions, but there's actually a different way to think about the problem. And you worked with this in pre-calc. I mentioned we have a quadratic divided by a quadratic. These two terms are going to dominate the numerator and the denominator. That's what gives you the shapes of the quadratic. That means your lower order terms, the 4x plus 2 and the 2 plus 4x, they really don't matter. So we can rewrite a limit problem a little bit more creatively. Basically, we're going to drop our lower order terms so that we can explore these problems. This gives us the limit as x goes to positive infinity, 7x squared over negative 3x squared, but x squared over x squared cancel out. This is why limits are so powerful. I love a good limit problem. We have 7 over negative 3. Oh, look at that. There's your negative 7 over 3 again. So if we drop the lower order terms, that's the same thing as multiplying by this 1 over x squared. Just a little bit more quickly, we can get to the answers. All right, so that's your right tail. Your right tail is going to the asymptote y equals negative 7 over 3. What about the left tail? All right, so if we drop those lower order terms again, we will now have the limit as x goes to negative infinity of our, the x squareds are going to cancel again. And we're once again left with negative 7 over 3. So this horizontal asymptote lasts on both the right and the left side of the function, and all is well. Okay, let's look at g of x for a moment. So g of x is a very similar problem. It's a rational, so if we write our limit, so let's do a limit as your x goes to infinity, so we're looking at the right tail, 7x squared plus 4x plus 2 over 2 minus 3x to the 8th. I could multiply by 1 over x to the 8th, but I think I'd like dropping my lower order terms better. So that gives me the limit as x goes to infinity. Drop those lower order terms in both the numerator and the denominator. I'm left with 7x squared over negative 3x to the 8th. All right, so do some division. This is our limit as x goes to infinity. 7 over negative 3x to the 6th. But you know that 7 donuts divided by an infinite number of people, nobody gets a donut. So the answer is 0 as we approach the right tail. So what happens on the left tail? Limit x goes to negative infinity. Drop your lower order terms, and we have, continuing to simplify, limit as x goes. Notice I'm using my limit notation, and you would better be doing that too. Write it every time until you substitute. Once you substitute, you are finished writing the limit notation. So what's the asymptote? Y equals 0. And that's a horizontal asymptote, just in case you forgot. All right, h of x. So we're going to do the right tail. limit as x goes to infinity. We're going to keep the whole function because I want to make certain that we're doing our problem using correct notation. We're going to drop our lower order terms, use our equal sign. This is the limit as x goes to infinity. 7x to the 8th over negative 3x cubed. Simplify. Looks like our right tail is going to have 7x to the 5th over negative 3. And now we're ready to substitute. And we will get a positive infinity over a negative 3, which gives us a negative infinity when we put it all together. So our right tail is heading downward. No horizontal asymptote. Now let's look at the limit as x goes to negative infinity. So the lower order terms have been dropped. We have 7x to the 8th over negative 3x to the 3rd. Wait, something different is happening here, where we will have our limit as x goes to negative infinity, 7x to the 5th over negative 3, and a negative over a negative is a positive infinity. So our left tail is heading upward, so it goes upward. So here we are for examples 2, 3, and 4. Now, as we look at example 2, what you should notice is that they all have a nice little sine function involved. Don't let the sign bother you. We're still going to follow the same idea when looking at the right tail of each expression. So the sine function was generally oscillating. However, because the angle is a bit fancier, maybe something fun's going to happen. If I look at the limit as your x goes to infinity for this function, we can actually drop our lower order terms within the angle. And when we do that, the 2 cancels and the negative 4x cancels. We're left with pi x squared over 3x squared. Now, the x squareds, of course, will also cancel out. Very convenient, don't you think? And we're left with the sine of pi over 3. And you should know what the sine of pi over 3 is. I'm not actually going to tell you just yet. I want you to be reminded of what the sine of pi over 3 is equal to. Now let's look at the limit as we go. Take x goes to positive infinity for our next sine function. When we drop our lower order terms again, we're left with pi x squared over 3x to the 3rd. And then, of course, the x squared and x to the 3rd cancel out, and we get the limit as x goes to positive infinity of our sine of pi over 3x. Now, just like earlier, the pi over x will go to 0 whenever we have x going to infinity. That leaves us with the sine of 0. And the sine of 0 is, of course, 0. Thought I'd leave you there? No, this time I told you. This next one, the limit as x goes to positive infinity. We're going to drop those lower order terms again, and that leaves us with pi x cubed over 3x squared. And when we cancel out our x squareds this time, the limit as x goes to positive infinity, we're left with the sine of pi x. Now there's that oscillating function that you were expecting. So this limit does not exist because the sine function is oscillating. Now when we look at example 3, we're told that we're looking for the limit as x goes to infinity for g of x and negative infinity. So it's actually 2 for 1. We want the limit as x goes to positive infinity, looking at the right tail again. And notice we have a natural log in here. That makes things way more interesting. So we have 5x minus the natural log of x. So I think the real question is, which term is the lower order term? And in this case, the natural log of x is a much slower turn as you go towards infinity, and it is the lower order term. So we get the limit as x goes to positive infinity of 5x over your 3x squared, which you know simplifies to the limit as x goes to positive infinity of 5 over 3x, which is, of course, 0 once again. So the tail end behavior goes to 0, or you actually have a horizontal asymptote at y equals 0. Now let's look at the limit as x goes to negative infinity. So I'm looking at the left tail of my problem. So consider g of x again. I'm going to start it again. We have 5x minus the natural log of x over 3x squared. So I've been a little bit neglectful. I've not been substituting. And if I were less neglectful, I would notice that the log of negative infinity does not exist. It is not in the domain. So we have a domain restriction here. And because of that domain restriction, we know that the limit does not exist. So we have to be a little bit more careful when considering functions that have domain restrictions. Speaking of domain restrictions, let's look at example 4. So here we are, we're looking at positive infinity. If I were to just substitute, I get the limit as x goes to positive infinity. Square root of 9 times infinity to the 6th power. Okay, that's gross. You should not write that. Let's think about it, though. This is what your mind is doing. So infinity to the 6th power is way more powerful than negative x squared or 2x. But in your denominator, you have a negative infinity. All right, so even though this is what my mind is doing, I should probably do some better algebra. So we get the limit as x goes to positive infinity. Dropping my lower order terms leaves me with 9x to the 6th power divided by negative x. Now I want you to think about the algebra involved here. When you take the square root of 9, you get 3. Of course you do. But then the square root of x squared, you might say is x to the 3rd power, but you would be incorrect. It's actually the absolute value of x to the 3rd. And here's why. The square root of x to the 6th is always positive. The x to the 3rd could be positive or it could be negative. The absolute value will force it to be positive. So when we simplify the square root of 9x to the 6th, it's actually 3 absolute value of x to the 3rd. And now this is divided by negative x. So essentially what you have here is x squared in the numerator, and your x in your denominator will cancel. And when you substitute, you get 3 times infinity squared over a negative. And so the answer is negative infinity. So think about that just a little bit more. That negative is very important. And remember that the square root of x squared is by definition the absolute value of x. Okay, so this is oddly specific, but set your timer. I want you to work on this next set of questions for 12 minutes only. There's a couple of hints for number 10. You want to rewrite as a rational. You're going to use that algebra idea for number 11, and the rest should be pretty straightforward. So pause now. Check your problems after you've given them a try. Check through your answers. Let me know if you're having any difficulties. All right, so our next couple of examples have to do with the indeterminate form of a limit. So sometimes simple substitution results in your indeterminate form. Indeterminate forms are your 0 over 0, your infinity over infinity, 0 times infinity. Oh, wait a minute. Infinity minus infinity is not always 0, by the way. 0 to the 0 power, 1 to the infinity, and infinity to the 0. So for all of these forms, strange things could happen. we want to come up with some algebraic techniques to deal with it. Always try substitution first. So for example, 5, I'm substituting. And when I substitute, this is what my mind is saying. Negative infinity plus the square root of the infinity squared. Ooh, so infinity squared. Basically, I've got negative infinity plus infinity squared, which seems to be 0, but it's not. So what we're going to do is a little bit of algebra. We're going to multiply by the conjugate. And when we multiply by the conjugate, we get 3x minus the square root of your 9x squared minus x over the same thing. So we write it twice so that we're multiplying by the number 1, our favorite trick. And keep your limit notation. Always write the limit notation. When you multiply through, this is now a difference of squares, which gives you 9x squared minus, and use parentheses, you have 9x squared minus x multiplied by itself, so the square roots will cancel out, divided by your denominator, which is 3x minus your square root, 9x squared minus x. All right, so we do some more algebra. Let's see here. We get the limit as your x goes to negative infinity. Your 9x squareds are canceling. You're left with x over. Now, just like when we were working with our earlier limits, do not simplify that square root on the denominator just yet. Let's get a little bit more analysis on this. So as we go to negative infinity, if we were to do substitution, the numerator is negative infinity, your denominator is negative infinity minus infinity. Now that's okay, because that's like minus 2 negative infinities. Okay, that sounds weird. So what we'll do is we'll drop the lower order term inside that square root, which of course is negative x. We have the limit now as x goes to negative infinity, x over 3x minus the square root of 9x squared. Now, the square root of 9x squared is the absolute value of 3x. Now, think about what's happening here. Essentially, you have an x in both the numerator and the denominator that can be canceled out. And you're left with positive 1 over 6, or negative 1 over negative 6, which is positive 1 over 6. So infinity minus infinity is sometimes 1 over 6. Think about that. So what happened if our original function went to positive infinity? Let's see what happens here. We would get infinity plus the square root of more infinity, and that would be positive infinity. All right, a lot less exciting, but that's what happens. So for example 6, once again, I try my substitution. I get infinity minus the square root of infinity squared, which we now know is not necessarily going to be 0. So let's multiply by the conjugate, do our algebra, due diligence here. Do not skip steps. The fun surprises could happen. So we're multiplying by our conjugate, and when we see what happens, we get our 4x squared minus the quantity 4x squared plus 1 divided by that denominator 2x plus square root 4x squared plus 1. All right, so what happens? The 4x squareds conveniently cancel out, and I'm left with the limit as x goes to infinity, negative 1 over 2x plus the square root of 4x squared. I could drop the 1. Oh, so essentially I have 1 divided by infinity, which you all know is 0. Ta-ta. So sometimes infinity minus infinity is 0, but not always. All right, you have 3 questions I want you to practice. Now only spend, let's be oddly specific again, 8 minutes on these questions, and then you can check through your answers. All right, so I haven't written the conjugate that you've multiplied by or the simplifications until the very last piece. So make certain that you understand how to complete 18, 19, and 20. So today's lesson follow-up is a little bit further in your book. Check out page 202, where you will talk about your horizontal asymptotes and limits as you go to plus and minus infinity. All right, guys, that is it for this lesson. You have an awesome day.